Yeah, thank you so much for the invitation. It's a huge honor to speak in this seminar. And okay, so I'll talk about scissors congruence K-theory for manifolds. It's mostly going to be joint work with Hoxima, Murray, Rovi, and Semikina. And then at the end, I will tell you about some newer work in progress with George Raptis and Julia Semikina. Okay, so this is a really fun project for me because I can finally draw pictures, which it's the first time that I can actually draw pictures in a talk. So let me start. So even though the talk will mostly focus on scissors congruence for manifolds, let me start with a very classical question about scissors congruence. So the classical question is about polyhedra. And it's, okay, given two polyhedra, P and Q, when are they scissors congruent? And what does this mean? It means that, well, we can write P into a bunch of pieces, and we can write Q, let's call this J, such that the pieces are congruent. And also we want the PIs and QJs to only intersect in edges and vertices. Okay, so in other words, well, in the plane, so we can think about this first in 2D. So think about polygons. So you can ask, okay, when can you cut a polygon up into pieces and reassemble the pieces into your second given polygon? And you might notice that for sure and certain, one of the invariants that you need your two polygons to have is that they have the same area. So we need P and Q to have the same area. And now you might ask, okay, is this the only scissors congruent invariant? And well, if you've never seen this before, well, you can think, what do you think? You might wonder in the beginning if maybe the angles have something to do, but you can convince yourself pretty quickly if you play around with it. So if you had scissors and a bunch of polygons, that you can always, there is an algorithm to always cut, well, as long as they have the same area, that you can cut a polygon into pieces and reassemble it into the other one. And so this is a very old classical theorem. So let me just illustrate it for you. So here's an animation, and there's a Git, there's this code on Git that lets you can draw any polygon that you want, and well, any two polygons, it will make them the same area for you, and it will play out this algorithm for you. Okay, so here there is one example of the Wallace-Bolyai-Gerwin theorem. Okay, great. So in the plane, there's only area. So you might ask about the next dimension. So what about dimension 3? And this is what's called Hilbert's third problem. So this was the third problem on Hilbert's list of problems. And it turns out that of course, in dimension 3, we still have the volume. So the question is volume the only scissors congruent invariant? That was the problem. And it turns out that there's more. So this was solved by a student of Hilbert, by Dan. So for dimension 3, the only scissors congruence invariants are, okay, so there's of course volume, but there's a second invariant called the Dan invariant. So maybe I won't define it for you, but it has to do with the angles. And so this is going to be an invariant that lives in R tensor R mod pi z. And I have just learned recently that apparently this paper of Dan is the first instance in math where the tensor product appeared, where it was defined the first time, even though of course he didn't call it the tensor product, but he basically defined the tensor product in order to define this invariant. Okay, so then invariants, well, maybe I can just tell you it's a sum over all the edges where you take the lengths, that's the part that lives in R, and then you take the dihedral angle at that edge, and you sum over all the edges. So you can generalize then invariance, and you have several then invariants for a given polyhedron in higher dimensions. So you can still ask this question, are then invariance and volume the only scissors congruent invariants? And okay, so now you can try to guess, are those the only invariants? Well, your guess is as good as anyone's. It turns out that this is an open question. Well, maybe the guess is that those are the only scissors congruence invariants. So this is a major open question. This is called Hilbert's generalized third problem. And there is a lot of exciting work in this area these days too, spearheaded by Campbell and Zakharevich. And now there's many people thinking about related problems. But for today, I'm not going to talk. So now I'm going to switch to manifolds. So inspired by this question, we can try to ask the same question in manifolds. Wait, sorry. Okay, so this was, sorry, the punchline that this is still an open question. Okay, so going to manifolds, we can ask, so I'm going to talk about compact oriented smooth manifolds. We can drop oriented, and we can do the same thing for unoriented manifolds. So the recipe for the cut and paste operation is start, and let me just draw this in an example. Let's maybe draw this in some other color. Okay, so first start to the smooth manifold. So let's maybe start with a pair of two tori. Then we're going to cut along a codimension 1 submanifold with trivial normal bundle. So let me pick here. So I'm going to cut. I'm going to make these cuts, and I'm going to cut out 2 disks out of this tori. Okay, and then the last step, we're going to paste back together. So we're going to paste back all the boundaries that we cut, but we can paste them along any diffeomorphism of the boundaries that we want. So here I'm just going to paste this to this, and I'm going to glue this to this. Okay, so now let's see what is the result. So I'm going to get a genus 2 surface and a sphere. Okay, so what we are saying is we're calling these 2 manifolds. Okay, let's go back to. We're going to call these 2 manifolds scissors congruent, or I'm going to explain on the next slide, Skk equivalent. Okay, so this is the recipe. So I'm going to keep the picture on the bottom of this Skk equivalence that we just saw, and now we want to make this general definition. So if I have some n and n prime that have the same boundary, and if we glue the boundary along some diffeomorphism phi, and if we instead glue the boundary along some other diffeomorphism psi, these are what we call Skk equivalent. Okay, so why Sk? So this stands for Schneiden und Kleben, which means in German, cut and paste. And also, well, this is a synonym, so we can call it scissors congruence. Okay, so the Sk is just historical because, okay, so as I will tell you on the next slide, this concept was introduced in the 80s in a book by Karas, Skk, Neumann, and Ossa. So this goes under the name the Sk book informally. And so, well, they are German, so they called it Skk equivalent, but it just means cut and paste equivalent or scissors congruent. And so in this book, so it turns out that the story for manifolds is a lot easier than for polyhedra. So in this book, they define scissors congruence groups. They define this scissors congruence relation, and they completely classify all the scissors congruence invariants. So it's much, much easier. And so it turns out that the only Skk invariants so it's all for closed manifolds in this book. So of closed and dimensional, so let's say oriented, but they also do the unoriented case. Manifolds are the Euler characteristic. And when this makes sense, in the dimension where this makes sense, the signature for oriented manifolds. So this is it. These are the scissors congruence invariants. And well, the approach, and this is also the approach for polyhedra, you can approach it algebraically and define a group. So for manifolds, the way we do it is, so we start with a monoid of diffeomorphous classes of compact, oriented, and dimensional manifolds. And it's a monoid and the direct sum. And then we can form a group that I will call Skn as the group. So first we take the group completion of this monoid. And in addition to the group completion relations that we have to mod out by, we also mod out by the Skk equivalence relations. And so these are the groups that, as I was saying, are fully computed in the Skk group. So unlike for polyhedra, where computing the scissors congruence group is a major open question in dimensions above 4. Okay, so we have these groups. So now let me switch gears. So of course, we're homotopy theorists. So what we want to do with this is really lift it to spectra. So let me give you a little bit of a brief history into the study of scissors congruent spectra. So this started with work of Zakharevich. So Ina, in her thesis and subsequent papers, look, well, and in case you don't know the story, I think the story was that she was actually literally teaching little kids in math circles scissors congruence in the plane, and at the same time learning K-theory and realizing that, you know, these relations, as you see that you want to mod out by, really do kind of look like K-theory. So so she tweaked and reinvented the definitions of K-theory to make, so she defines a scissors congruence K-theory spectrum. So via the notion of what she called an assembler. So what this is, it's, I'm not going to give the full definition since we're not actually going to use it. But so this was the first construction of scissors congruence K-theory. So this is a Grothendieck site plus some extra data. So what it is, it's really it's a category where you have a notion of covers of objects, and you can axiomatize this notion of covers so that so basically cut and paste data, and then you can build a spectrum out of it. And what it recovers on pi naught, so she recovers on pi naught the classical scissors congruence groups for polyhedra, I should say. Okay, so this construction lifts the scissors congruence group for polyhedra, and also a main example of interest for her was K naught of varieties. So this is again a very classical group. It's the Grothendieck group of varieties. So this is the free abelian group on varieties where you mod out by a relation of the form x plus y minus x is equal to y if you have a nice immersion of x into y. So as you can see, it looks a little bit like K-theory, except what you're modding out by doesn't look like an exact sequence. It looks more like a subtraction So not addition, it looks more like subtraction. So this was not the only construction. Then Campbell, independently inspired by Ina's work, defined another kind of machinery for building a K-theory spectrum, a cut and paste K-theory spectrum that applies to varieties. So he defines subtractive categories. So categories with notions of what he calls subtractive sequences as opposed to exact sequences. And he builds also a K-theory spectrum. And okay, so this also recovers K0 of varieties on pi naught. And you might wonder, well, they have these two different constructions with even more constructions and more general constructions. They can show that with a lot of work that their K-theory spectra of varieties do indeed agree. Okay, so all this machinery was really geared towards variety. So this was the main example of interest for them. Okay, so now our goal in this project was, so the question was, can we construct a K-theory spectrum of n-dimensional manifolds that has pi naught, the classical Skn group? So, and wondering if we can use some of this machinery to build such a spectrum. So the first issue that shows up as we start thinking about this is that, well, of course, the pieces in a cut and paste. So if you think about polyhedra, if you cut a polyhedron into subpolyhedra, the pieces are also objects in your category. Same for varieties. If you cut the varieties into subvarieties, you still have varieties as your pieces. But here, the pieces in a cut and paste, well, they need to be objects in your category. So as I was saying, classically, the story was for smooth manifolds. So if we cut a smooth manifold into two pieces, the pieces are now manifolds with boundary. So yeah, so if we want to make this work, we need to work in Mn boundary. Okay, so so in order to solve this problem, okay, so solution to issue number one is, okay, so we're going to make a new definition. So for M and N manifolds with boundary, we're going to define the cut and paste relation. Okay, so we're going to define it the same way, except paying attention to the following, imposing the two following conditions. So such that, so first we want to not allow to cut any of the boundaries. So do not allow boundaries to be cut, and all cut boundaries are required to be pasted back together. Okay, so note that this is a choice. So the second choice, so I guess the first one makes sense, right? Like we don't want to cut along the boundaries and introduce corners or anything like that. But the second one is really a choice. So we could, there would have been the option to allow to cut boundaries and allow them to stay cut, because now we have manifolds with boundaries. So that could be fine. Okay, so we're going to define now the Skk boundary group to be the group completion of the monoid of manifolds with boundary mod, also this Skk equivalence relation. Yeah, so the remark is that, so also in the escape book, even though it's really mostly for closed manifolds, they do go on some tangents in some later chapters and propose, some different scenarios that you could consider. And one of them is manifolds with boundary, but they don't really spend a lot of time thinking about it. And the proposed definition there is actually a little bit different than ours in this regard. So this is different than the SKN boundary proposed in the SK book. So the difference is, so this is a small warning. So the difference is precisely this, that they let, so these two manifolds pasted together, they allow this to be SK equivalent to M1 disjoint union M2, to not paste the cut boundaries together. So we do not allow this. And of course, the first thing we thought about the definition, but the conclusion is that that's not going to work for K-theory. So what we're doing is really, and we also want to stay as close as possible to the classical SK spectrum. So we're really, the boundaries that we're allowing, like, they really don't interact at all with the cut and paste. So we're not introducing new boundaries, and we're not allowing to cut along them. And we're also, so every cut and paste operation will end up with whatever boundaries you started, that those are the boundaries that you end up with. Okay, so for this, in order to really solve this problem, okay, so we made a new definition, but we want this to be as close as possible to the classical SK group. So the first theorem is that there is a split exact sequence that relates these groups in this way. So let me maybe say, okay, first let me maybe say what this is. So this is just the Grothendieck group completion of the monoid of diffeo classes of null cobordant n-1 dimensional manifolds. And let me maybe also write what these maps are. Okay, so here we start with a class of some manifold M we just included. So we view a closed manifold as a manifold with boundary. And here we take a manifold to its boundary. Okay, so now let me just give, so as I was saying, this is why this is exciting. You can actually draw pictures and do proof by picture. So let me just give the proof idea for exactness at one spot. Well, just one inclusion, why the kernel of beta is included in the image of alpha. And I'm going to do, well, not give you the full proof of even this, but just do a picture, just do one example to illustrate kind of why this is true. Okay, so what does it mean to be in the kernel? So you have to be a formal difference of things that have the same boundary. So let's pick these two pieces. Okay, so this is something, an example of something in the kernel of beta. And in order to show that it's in the image of alpha, I need to express this as a formal difference of closed manifolds. So my claim is that, okay, so the claim, or actually let's write it below. Okay, so the claim is that this is equal to the formal difference of, no, sorry, not this, the sphere minus the torus. Okay, so the proof of the claim. Okay, so now we just need to do a cut and paste. Okay, so what I want to show is, so let me write everything with pluses so that we have disjoint unions. So I want to show that this plus the sphere is equal to the torus plus this cap. Okay, so I need to do some cut and paste operation. So let's see, I can cut a little collar from there, and I can cut this in the middle. Okay, so what do I get here? I get this little collar plus also just this cap. And here I get the two caps. Okay, so now I'm just going to paste them together. Sorry, this should have a hole also. So now I paste them the other way, and you can see that now I get exactly what I wanted. Okay, so right, so when I paste this, I get this little cap, and then when I paste these things together, I get the torus. Okay, so these are indeed Skk equivalent. So I do have such a relation. Okay, so we have this exact sequence. And so this tells us that this SKN boundary is a good candidate for a group that now takes into account manifolds with boundary and Skk group, and it's related to the classical SKN via this exact sequence. So the new question now is, well, can we recover SKN boundary as a pi naught of a K-theory spectrum? And now we run into issue number 2, which is that, so if we try to use the machinery that I described before, well, assemblers or subtractive categories, so these do not work. Disappointingly enough, if you try to use to look at the axioms for these kind of frameworks, this does not work. And the problem is, so it's similar in both cases. So for example, for assemblers, as I said, it's a category with notions of covers. But one of the axioms is that every cover needs to have, any two covers need to have a common subcover. So for example, let's say I cut the sphere like this, and then let's say in another cut, so another cover, I cut it like this. Well, now if I look for a common subcover, this is not good, because now those 4 pieces would be manifolds with boundary. So the problem is that covers do not have common subcovers. Okay, so let me describe a little bit the philosophy behind this problem, since I think that's enlightening. Maybe let me write this in a slightly different color. Okay, so classical algebraic K-theory of exact categories or Waldhausen categories of stable infinity categories. So this is all defined via the S dot construction. And what it does is it encodes relations of the form A plus C is equal to B for exact sequences. So for exact sequences, A to B to C. So what algebraic K-theory does classically is it breaks off exact sequences, so very concretely on K naught, and then it does this via the additivity theorem, like on the higher homotopical level. So then what these different frameworks that I was describing of assemblers and subtractive categories, what these do is they encode relations of the form. So I will write the same thing, A plus C is equal to B, but now this is going to be for subtractive categories. So these are, sorry, not categories, subtractive sequences. So these are sequences of the form A goes to B, and now this arrow goes the other way, so C also goes into B. So think about varieties, right? That's what you have. X goes to Y, and then Y minus X also goes to Y, and they were designed for this purpose. So what we really want, to encode relations of the form A plus B is equal to C plus D for squares. So for some kind of squares, A to B to C to D of this form. And all of these frameworks before, so they're not powerful enough to encode such relations. So as you can see, both so exact categories and subtractive categories are particular examples of what you might call squares, right? So if you put a 0 in one corner, you can recover both exact sequences and subtractive sequences. But we want the full power of being able to break up square relations. Okay, so this So what the framework that we're going to use is that of the K-theory of categories with squares. So this is also after Campbell and Zakharevich. They also came up with this definition, but this had not even been written down, or well, except some small drafts. So this is, I think, except in our paper, it still has not appeared in print. So this was not as well developed or had been used because yeah, in their work before, they were focusing on the example of varieties for which the other frameworks work really well. But they had thought about this definition in their many years of thinking about K-theory frameworks as kind of the most general framework for algebraic K-theory. So let me just give you the definition since it's very simple. So a category with squares, and you have all seen the definition of a Waldhausen category at some point, so it's very similar. So a category with squares, so it has a notion of cofibrations, but also a notion of a second class of maps that maybe we want to call cofiber maps. But then it also has a class of distinguished squares. So some commuting squares that we call distinguished, such that, and now there's 4 very simple axioms that need to hold. We want C to have coproduct, and the squares, we want this to be closed under coproduct. Then 2, the squares need to compose horizontally and vertically. Then number 3 is so just like in the case of a Waldhausen category, we want these 2 classes of special classes of maps to contain all isomorphisms. And lastly, if both, so if we have, okay, I don't know how to say it. So if we have a commuting square and if both parallel maps in a square are isomorphisms, then the square is distinguished. So let me maybe use this notation. So it's one of the squares that we denote by little square. And they did not require this in their definition, but it's something needed for the K-naught computation. So I would also like to require that, well, we have an initial object. So maybe let's call it O or something for, let's say, the first class of maps, the horizontal maps. Okay, so we want to have some distinguished object where we're going to base the loop space that we want to build. So that's it, the axioms. So given these axioms, let me just now give the definition. So we can give the definition of the K-theory space. So this is just going to be the loop space based on this designated object, and it's going to be the realization of a bisimplicial set, and the bisimplicial set is just the set of P by Q grids of distinguished squares. Okay, so A1P, okay, and going down, A21, okay, and so on. So all of the squares are distinguished. AQ1. Okay, so everything here is distinguished square. Okay, so now the theorem of Campbell and Zakharevich was that exactly this definition, that K-naught square of C is the free abelian group on objects, well, objects of C, mod the relation. Okay, so this designated object that I was denoting by O, this is going to be the 0 in your group. And also the relation that we mod out by is exactly the square relation that we want. So A plus D is equal to B plus C for a square. So A to B to C to D. And also, I would say, so they hadn't computed this, but it is not very hard to see also that this is an infinite loop space. So it really is a spectrum with this pi naught. Okay, so given this framework, now we can try to apply it to manifolds. And so the definition that we gave is, so we define a category of manifolds with boundary as a category with squares. And I drew this little picture so you can keep this in mind. So those are the squares the kind of squares that we want to have in this category. So first, this designated object is going to be the initial object, just the empty manifold. And then what's going to be a little weird here is that horizontal and vertical maps are going to be the same class of maps. So horizontal and vertical maps, we define them to be the same class, and it's going to be smooth embeddings, so M into N, such that, and we just want these to be nice inclusions of pieces. So we just have to be careful about the boundary. So the boundary of M, we want this to map to a submanifold of N with trivial normal bundle. And also we want to make sure that each boundary piece so let's write it like that. Each boundary piece goes, so maps entirely to the interior or to a boundary piece. Or, okay, so I drew the picture. This is the picture that, okay, one more thing. So what are the, okay, so far we said what we want the horizontal and vertical maps to be, and we want them to be inclusions of subpieces of manifolds. And lastly, the distinguished squares. Okay, so now I'm not gonna use the co-fiber notation, so that I'm gonna use different notations for these kind of horizontal and vertical maps, but I'll try to switch the notation a little to indicate that all of these are now embeddings. Okay, so M. Okay, so the distinguished squares are the push-out squares. So squares of this form that are also push-outs. So just like in the picture. So even though these maps are defined to be the same class of maps, you really do have to be very careful to keep them separate. Well, in your constructions, they are two different kinds of maps that you cannot compose when you form that bisimplicial set. Okay, so now, so the first theorem is that manifolds with boundary, so with this definition that this is indeed a category with squares, so it satisfies all the axioms. And also, so the K naught that we get via the theorem that breaks off the square relations, we can show, sorry, manifolds with boundary, that this is indeed isomorphic to SKN with boundary. And second, what we can show is that there exists a map of spectra from this square K theory of manifolds to K of Z, which on pi naught agrees with the Euler characteristic. So what happens on pi naught, it sends the class of a manifold to its Euler characteristic. So maybe I could say like one or two things about, well, what goes into the proof. So it's really quite nice once you set it all up, it becomes very easy. So the thing here really to set up carefully is how do we view, so the target was K theory of Z. And well, a priori, that's not a category with squares, but well, so the proposition is that if C is a Waldhausen category, we can define C square with, so the cofibrations are the cofibrations. The cofiber maps, we can let these be all maps. And the squares, A to B to C to D. Okay, so this is going to be squares that are homotopy pushouts. So where the map from the pushout is a weak equivalence. So this is how weak equivalences get encoded. So the claim is that then this is a category with squares. So this is how you recover Waldhausen, K-theory Waldhausen categories. And K of C is K-Wald of C. So it's the classical S-dot construction. And this is really secretly due to Thomason, and it shows up in Waldhausen's paper. Of course, they don't talk about categories with squares, but Thomason had this alternative construction of the S-dot construction, which is basically this. Okay, and then the rest of the idea of the proof is, well, reduce to Meyer-Vietoris. So now that we have that, we can form the target as a category with squares. And this is, so there's several ways actually to make a Waldhausen category in the category squares, but this is why it's important to use this one where the the vertical maps are all maps, because we want squares to map to squares. And then, well, we take singular chain complexes and so on, and then we'll play the usual game, and we see that on K0 we really do get the Euler characteristic. So now let me just say in the last minutes, let me talk about, well, some recent work and some questions that were, okay, of course, one of the big questions is what are the higher homotopy groups? And well, and what higher invariants do they encode? So for example, even for this map on pi naught that sees the Euler characteristic, what does it see on higher homotopy groups? And so there's another definition which is more refined, which we have thought about a bunch. So it's very tantalizing. So there's something called Skk equivalence, which, so the extra K stands for controllierbar. So this is like controllable cut and paste. So the idea is to keep track of gluing diffeos. So the exact relation that you want to mod out by in order to form this Skk group is, so if we have M1 and M1 prime glued together and via some diffeomorphism, so M1 and M1 prime glued together via some other diffeomorphism. Okay, so in the Sk group, this would just be 0, right? We glued two pieces via different diffeomorphisms. That's exactly what we want to set equal. So in this Skk group, this is not 0 anymore. It's just equal to, so if I have any other two manifolds, M2 and M2 prime, that have the same boundary as M1 and M1 prime, and they're glued according to the same diffeomorphism, then I just want these two things to be equal. So basically, I just want this to just be a function of just the gluing diffeomorphisms and not depend on the manifolds. Okay, so we have this Skk group. So this gives rise to the Skk group. So this is Grothendieck Mn, and this is all for closed manifolds. And the great thing about this, well, I'll write equal, but this is really a bunch of work to see. So this is pi naught of the MTSO spectrum. So this is pi 1 of the coordinates category. So this group is very interesting. And okay, so the question is how does it relate? And well, there's many things that seem to not work. So remember, this is for closed manifolds. It turns out if you try to make a similar definition to what we made for manifolds with boundary, it actually reduces back to the SK boundary group. So when you have boundaries, kind of everything collapses, and this extra relation doesn't give you anything. So it seems subtle, but one thing, so that was kind of disappointing for a while, and I still don't know how to make sense of Skk with boundary. But so I'll just end with this theorem. Maybe I'll put it in quotes since it's work in progress. So this is together with Raptis and Semikina. And we do compute something here because I know this is supposed to be computational. So we are going to try to compute some elements in K1. So let M be odd dimensional. So now I'm going to be in the unoriented case because, well, so it might have but we're going to just do the scissors congruence of unoriented manifolds so that we allow ourselves in our category to have orientation reversing diffeomorphisms. So F, I want this to be an orientation reversing diffeom. And now the claim is, so I'm going to look at exactly the map that we had before, the map of spectra that on pi naught gave us Euler characteristic. And we're going to analyze what happens. So K1 of Z is Z mod 2. So what happens on K1? So we cannot fully compute K1. I'm definitely not claiming that, but we can show that M common automorphism of it does represent an element of K1, as is usually the case. So we can very concretely construct this element in K1. And we can track where this maps to. And this is just a computation. And so it seems almost like a coincidence, but it's really cool. It looks like what we get as an invariant in Z mod 2 is what's called the Kerver semi-characteristic. And the reason why I think this is so cool is that, so this is the one of the main examples of Skk invariant. So this is an Skk invariant that's not an Sk invariant. So it looks like on pi 1, we can detect Skk invariance. So yeah, many puzzling questions here. So I will end here, and then